All right, good afternoon, everyone. We shall start. So first of all, today is the due for homework 3, and we have extended for 2 days for the due. So I believe that should be enough. But of course, if you can stick to the original due, you again will get bonus. And we also released the homework 4, which is to ask you to review and understand, various inference stuff. We mentioned that is our discussion, previous in the last few lectures. Okay, so in the last lecture on Tuesday, we started talking about Markov chain Monte Carlo sampling algorithm. Right, there's another branch of techniques to approximate posterior distribution given some probabilistic model. Right, so the idea is different. Right, so the strategy for Markov chain Monte Carlo is to construct a Markov chain, right? So a Markov chain, you can view like, okay, I'm gonna keep sampling a sequence of random variables, right? And the most important property of Markov chain is called like short-term dependency, like, namely that if I want to sample a new state, given all the previous sampled states, this conditional probability only depends on the last state, that is the n. Right? This is called a Markov property. Right? That's very good, and this looks a very, bold assumption or simplification. But actually, I think the most frequently used assumption in engineering, scientific, in weather forecast, all kinds of stuffs. So that means you actually, in most cases, you really don't need to account for those long-term dependencies. And you just use short-term dependencies that happened like a moment ago, that'll be enough. Okay. So regarding Markov chains, their properties and their mathematical properties, theories that there is a huge topic. Markov chain is not only used in sampling techniques, it is widely used in many other engineering applications, like signal processing and so on. Right? But here, Markov chain is served as a fundamental tool for us to approximate to the posterior distributions. So the goal is that we're gonna, in approximate Bayesian inference, the goal for us is to construct such a chain who is ergodic. Ergodic means that, okay, this chain, no matter starting from whatever initial distribution, you just keep sampling, and in the end, or at the limit, the marginal distribution of your state will be stable, and it will be exactly one distribution. Right? And second thing is that we're going to construct the chain, meaning in the design of the so-called transition kernel. Right? Transition kernel is just another notation of this conditional probability. We want to smartly design such a transition kernel such that the stable or stationary distribution this chain converges to is exactly the target posterior we want. Right? That's the idea of the Markov chain Monte Carlo. And in most cases, you don't need to worry too much about the ergodicity unless the thing is a little bit special. So basically, ergodicity says that your chain, suppose your state space, right? The chain that no matter from whatever state value, you have the positive probability to jump to other distinct state and across the whole state space. It basically means, okay, I can start from any value in this whole state space, jump to any other value within finite number of steps. So that guarantees that your sampling, in theory, can explore the full space of the random variable values, so that in theory, you can recover all the modes in your posterior probability. So for example, this is your posterior true posterior distribution, right? If your chain doesn't satisfy ergodicity, that means so. And just to highlight, in our case, the whole sample space is just this ruler. If your chain is not ergodic, then it's possible that it's gonna when it jumps to some sub set of the sample space, right? That means one segment of this line, it might not be able to jump out. This is not what we favor, although even if your transition kernel is valid, it can generate a bunch of samples which will approximate. If you draw the histogram, approximations will approximate to this mode, but it's not sufficient, right? So we want our chain to be able to generate samples across the whole domain of the random variable values, so that in theory it can capture all the modes in the posterior distribution. Right? But as we mentioned, there's some problem of a Markov chain. Like although in theory, even it is an ergodic chain, guarantees to exactly recover the whole posterior distribution. In practice, once it enters into some mode, it's very hard for it to get out. That means you need to spend a lot of samples, a lot of cost to jump out this mode and enter into the next mode. That's a practical issue. That's not the theoretical issue. Okay. So conceptually, once we have such a chain, we just run our sampling procedure to generate a bunch of samples. And our sampling will contain two stages. One stage is called before burning. So before burning means that the chain has yet converged to the invariant distribution. That basically means the chain has yet converged, right? Has yet reached the stationary distribution, and it's still exploring space, and the marginal distribution of the state is still varying. Right? So in practice, we usually set up a maximum number of steps before burning. Basically, conceptually, there's such a stage that before burning, your chain doesn't converge, but after burning, the chain has converged. That is conceptual existence, but in practice, it's very hard to know if it is really in burning stage, right? So in practice, we just set a maximum number of steps, like 10,000 or 1 million even. Right? But there are some tricks, heuristics to verify the convergence empirically. Again, this is not guaranteed, but it can give you some hint. Like most commonly used is called trace plots. So what does trace plots means? So suppose this is your random variable, right? You want to compute the posterior distribution of Z given the data D, right? And if you want to look at if your chain has converged or not, you can look at each element, like Z can be viewed as Z1, Z2, pick up any element, ZG, right? You just look at, along with the number of samples, right? number of iterations, number of samples, right? How the value of ZG varies. So if it is it converges. If it converges, means that the distribution of ZG becomes stable, right? And then you can imagine that at the beginning, because the distribution is kind of varying, so you can see this wild perturbation, right? But once it reached the burning stage, right? Because the distribution of ZG is kind of fixed, you should see some clear patterns, like something like that. That basically means your estimated posterior distribution is kind of a high density region in this particular range. Right? That's why your sampled ZG is kind of like inside this high density region, but it's kind of like wiggling, right? And but this is not. This is not guaranteed. It's possible like you have your you maintain a stableness for a while, but then your stationary distribution, your marginal distribution of the states in the chain is kind of swift, right? Changed. But in most cases, like you can use that to kind of exclude the situations where you're still you have yet reached the burn-in, because if you haven't reached the burn-in stage, the trace of the ZG can be much more wild. Okay. Any questions so far? So trace plot is kind of standard techniques to give some heuristic diagonals of the convergence. So once you see your ZG is kind of perturbating in this way, or have some very clear patterns, right? If this has two modes, it might be something like that. And then if you look at the clear patterns like this, well, you might have like much higher confidence that it has already converged. But again, it's not guaranteed. And usually, if you can see these patterns in practice, you can just use those samples to make predictions. You'll give you good results. Okay, so this is a stage called before burn-in, right? Then after burn-in, we believe that the MC Markov chain has converged. Then we generate the posterior samples. Right? We use our sampler, use our current chain to generate samples, and to reduce the strong correlations, as we mentioned, right? The chain, because each sample, like Zn plus 1, is sampled conditional on the previous sample. So among the samples, between the successive samples is very strong correlations. Of course, I don't want so strong correlated samples. I want to reduce the correlation. How can we do that? We can take a few samples, right? Like every 5 samples, every 10 samples, every 20 samples to reduce the correlations. But again, there's still correlation. Right? So there is some kind of empirical estimate or approximation of the so-called effective sample size to say how many, this set of Markov chain generated samples is approximately equal to how many independent identical distributed samples. Because those samples because these identical distributed samples are more informative than those correlated samples, right? Like you might generated 1,000 MC samples, but because the high correlation is among those samples, they actually contain a lot of duplicated information. So people are more interested in that. Okay, if I just want to measure them in terms of independent samples, how many independent samples they approximately equivalent to? Right? There's a formula it's called effective size that can give you an answer. And maybe you can use your 1,000 samples collected from your Markov chain, and after calculating effective sample size, it'll tell you just it is 50. That means okay, this is just equivalent to 50 independent samples. And then you might need to draw more, like for 200 samples, and you calculate around 100. Okay, 100 is in many scenarios, many tasks they're good enough. Okay. Okay. Any questions so far? Okay. So now we have given a sufficient background introduction and like overview of Markov chain Monte Carlo ideas. Now we're going to talk about several typical algorithms in detail. The first one, and also most fundamental one, is called Metropolis-Hastings algorithm, and people often call it MH. As MH is it's kind of like so fundamental. You can view almost all Markov chain Monte Carlo sample as a kind of special variant of Metropolis-Hastings. Okay, so let us look at Metropolis-Hastings. It is a general framework for Markov chain Monte Carlo sampling. So to generate a sample, right? That is to generate a value of the next state in your chain. Okay. Metropolis-Hastings conduct two steps. The first step is called the proposal generation. That means we're going to use some proposal distribution to generate a candidate. Note that the candidate is not necessarily the final state in our chain. It's possible not. So once we got our candidate in hand, then we'll do a test. It's called acceptance test. We'll test if this candidate should be accepted as the next state in our chain. That means a possible sample of our posterior distribution. If it is not, then you have to discard this proposal and then use the current sample as my state. So how can we fulfill these two steps? So first, you need to select a proposal generation distribution. But again, I want to emphasize, the proposal distribution is not the transition kernel or transition or conditional probability to generate the next state given the current state in the Markov chain. It's just one part of it. Right? So we denote this proposal distribution by Q. Of course, it's still a conditional distribution. You generate the candidate Z prime given the current sample Zn or current state Zn, your chain. For example, a very commonly used proposal distribution is just Gaussian. Given Zn, you're just using Gaussian to sample Z prime, where the mean is Zn itself. So it's basically like you're gonna random perturbate Zn, right, to find one candidate. So you sample this proposal Z prime first, and then we're gonna use one probability to decide whether we should accept Z prime as our next state of your chain or not. So what's the probability to accept that? It's like you toss a coin, and in most cases, the probability you see the head is not 0.5. The probability you see the heads is actually calculated in this way. So you're gonna calculate a fraction, right? A fraction that is dividing the proposal distribution condition on Z prime to sample Zn times the joint distribution of Z prime and theta D divided by you sample Z prime given Zn with your proposal distribution multiplying your joint model probability using Zn as your model parameter value. So there's an intuitive explanation. It's like, okay, the numerator, the denominator, we should start with denominator. The denominator is like, okay, given the current state in your chain, right? Zn. I'm gonna first sample the proposal or the candidate Z prime, and then multiply the probability that you evaluate your model with Zn. And this is called like jump out. Right? So because this joint distribution is proportional to the posterior, right? It's like, okay, suppose I'm gonna use my true posterior to sample Zn, and given Zn, I generate Z prime, this whole probability. And the numerator is like, okay, I'm gonna use Z prime. I'm gonna first generate Z prime according to the true posterior, and then given Z prime, I use my proposal distribution to generate Zn. It's like a jump back, right? And if this ratio, and then we'll look at this ratio. And if this ratio is bigger than 1, then we just accept it. Otherwise, if this ratio is less than 1, like say 0.6, right, we just take a 0.6. We use that chance to toss a coin and then to decide whether we're gonna accept the Z prime or not. So it's kind of heuristics. But this heuristic is easy to memorize. It's like, okay, this is Z prime, this is the N, this is Z prime, right? So I just look at the probability you jump back from Z prime to Zn, divided by the probability you first generate Zn, then generate Z prime gives Zn. You see this ratio, right? And if this ratio is bigger than 1, okay, you just accept Z prime. If this ratio is not bigger than 1, then you take that ratio as a chance to accept Z prime. So in practice, how shall we implement this procedure, right? So to implement that, most common method is that, okay, I'm gonna take a logarithm because you don't want to really evaluate a drawn probability. It can be very, very small. Right? So you take a logarithm, you make numerical things much more stable. So you take a logarithm of this guy, and it is equivalent to, let me put it in this way. You take a logarithm, you take exp. These are same thing, right? And then you can move logarithm inside this mean function. So you got mean of 0 and the mean of the log numerator subtracted the log denominator. Right? Then you take exp, you got this probability. And then how do you fulfill that? You toss a coin with that probability to accept Z prime. Just sample uniform random variable. Right? And if this random variable less than or equal to this probability, you accept Z prime. Otherwise, you don't accept it. Why this is correct? I mean, why doing this is correct?
The chance that it happens is the same as the solution.
Yes, exactly, right. I just want you guys to double check, right? So if you denote the right-hand side is just this guy, right? Just this guy. And that means you have a probability P to accept Z prime. And if you do this, right, if you sample a uniform random variable U in 0 and 1, you just check if U is less than or equal to P. If it is, we accept, otherwise we reject. We can look at the probability you accept, right? That is actually like P, U less than or equal to P is actually an integral, right? So it's from 0 to P, and the probability of U in this integral, right? And the probability of P of U, it is 1, right? It's uniform distribution. It's just 1. So the unique is simply P. That is why it is correct. Any questions so far? Everyone is comfortable? Okay. So I just kind of suggest you to verify this because when I learn this, like I try to show every step is correct. Okay. So if we accept Z prime, that means we can safely assign our next state to be Z prime. Otherwise, if we reject Z prime, we're gonna set the next state, Zn plus 1, just equals to Zn. That means we didn't generate new samples. We still maintain the same state in the chain. And that means if you look at the history of this chain, it may contain many, many duplicated samples because of the rejections. So, okay, I want to first guarantee everyone knows these 2 steps, right?
Why do we have to reject? We can just wait at the state we are until we
That is called Z. That is conceptually to generate the same state, like generate next state which is equal to Zn. I mean, in practice, of course, you can just maintain that. There's no issue for that. Yeah, you don't need to explicitly repeat it. Right? But conceptually, you need to say because you're every time you just generate next sample, generate next sample, generate next sample. Right? But in practice, of course, you never need to really store those duplicated samples. Okay, so now everyone is clear about these two steps, right? We're gonna first come out a proposal distribution, which is pretty free, right? You condition on your current state in your chain to get a candidate. Then you run an acceptance test. Of course, it's a random test. Right? You use your candidate and the n to calculate this ratio and take a mean between this ratio and 1 and use that probability to accept your new candidate. Okay. If it accepted, well, that's good. That means your next step is a new candidate. Otherwise, you just maintain the same state. So now we want to see why this is correct. So basically, we know that the conditional probability or the transition kernel is actually fulfilled by these two steps, right? We just want to show that this transition kernel can maintain the invariance, meaning that it can guarantee that the true posterior distribution is invariant to this transition kernel, so that we can show that your chain actually guarantees to converge to the true posterior in the limit. Right? So we're going to use detailed balance to show that. Right? So we know that if a transition kernel satisfies the detailed balance with respect to any distribution, that means that distribution is invariant to this transition kernel. Or in other words, this chain will finally converge to that distribution. Right? So now we consider arbitrary two successive states, Zn and Zn plus 1. Right? We consider the first case where there are two different samples. I mean, their values are different. So Zn plus 1 is not equal to Zn. They will know that Zn plus 1 must be generated from accepting some proposal. Right? Then we want to look at what is the transition probability or the condition probability you generate Zn plus 1 given Zn. So this probability actually consists of two steps. First, it is a probability that your Zn plus 1 is sampled, indeed sampled from this proposal distribution. And next, given your Zn plus 1 is your candidate, they accept Zn plus 1. And the probability you accept that is this guy, right? Is mean 1 and fractional, right? So we observe that in a numerator and denominator, they're both joint distribution of your model, but the value of your random variables is assigned as Z and Z plus 1. Right? So because we want to look at if this transition kernel is invariant to the posterior distribution, so we can divide both joint distributions by the marginal distribution of data, right? Or the model evidence. Right? It doesn't change because we divide the same thing both numerator and denominator, which ends up with this fraction. Right? So you can see that with a posterior distribution of Zn plus 1 given D times this proposal generation divided by the posterior distribution of Zn given D multiplying with this proposal distribution. Right? And in the outer level, right, the outer level who multiplies with me is actually this proposal distribution, which is Qn Zn plus 1 given Zn. Right? So next is quite straightforward. Right? To check the detailed balance, we need to multiply the true posterior with the transition probability. Right? So we'll look at if you sample your Zn from the true posterior, and then given Zn, you sample Zn plus 1, what is the joint probability? Right? So here is a true probability, and here is something we just obtained in the previous step, right? Now, what we can see is that this guy outside of me is the same as the denominator in the second argument of the mean function, right? And again, because this guy is positive, so you can just multiply into this mean function. So you got your joint probability is actually the mean of these two probabilities. Okay? The first probability is just this guy, right? P of Zn given D, and then the proposal probability given Zn, we generate Zn plus 1. And the other guy is the numerator here. Right? I will make it clear. Right? So it's just the mean of these two probabilities. So now, to check the detailed balance, right? We want to check if you sample your candidate from the true posterior distribution, and then from your candidate to sample Zn, what is the joint probability? You want to see if these two probabilities is the same, right? So if you do this, actually you don't need to go through these two steps again, because there's symmetric, just to swap the n and n plus 1 to get the joint probability. Right? And in this case, you just swap n plus 1 in this case. Does it change the value? It doesn't change at all. Right? That means you just if you swap n plus 1, it just means you switch the two arguments of the mean function. It won't change at all. Right? So in this case, we know that these two joint probabilities are the same, right? They satisfy the detailed balance in this case, where Zn plus 1 is not equal to 0. Any question? Yeah, I guess this is straightforward. But if you feel like a little bit uncomfortable, you can just look at slides and derive something by yourself. It's really something very basic. And then we need to look at a small corner detail where what if your Zn plus 1 is the same as Zn? They are identical. So we want to look at the transition probability. In this case, that means you start from Zn, you generate Zn plus 1, whose value is identical to Zn. This probability actually consists of two mutually exclusive cases, right? One is that, okay, you generate a new proposal, yet it is rejected, right? A second thing is that you generate proposal Zn plus 1. However, this proposal is the same as Zn. And even better, it passes the acceptance test. It sounds a little weird, but there could be such kind of case. Right? We just need to look at what's the probability, what's the summation probability of these two mutually exclusive events, right? So, so first of all, if we look at starting from Zn, right? That means you're going to first sample Zn from the true posterior distribution, and then sample Zn plus 1 given Zn. So you're going to multiply a true posterior, and then multiply this transition probability consists of two parts. One is you reject whatever proposal you generated from your proposal distribution, or you generate your proposed candidate is the same as Zn, and it passes the acceptance test. Right? So if you want to contrast this joint probability with this reverse side, so mean that, okay, I'm gonna sample Zn plus 1 first from the true posterior, then given Zn plus 1, you sample Zn, But remember, in this case, Zn plus 1 equals to Zn as well. So that means the posterior part is the same because Zn equals to Zn plus 1. And in the transition part, again, because Zn equals to Zn plus 1, so given Zn, that value you reject proposal is exactly the same is as given Zn plus 1, you reject the proposal. And similarly, because this guy, these two guys, the value is the same, so this whole probability is the same. So it's very trivial to say actually the D2 balance is also satisfied in this tied case. But again, this is just to make your whole arguments and whole proof more rigorous. Although this is a very trivial case, but you need to you should consider other possible cases. Okay. So now let us consider a common use case, a common use proposal distribution, as we just mentioned. We often use a symmetric proposal distribution, like a Gaussian distribution, right? So given Zn, I'm gonna use Zn as a mean and to sample a Gaussian proposal, right? If we're doing this, and then we can take a look, what's the acceptance probability, right? So because this proposal distribution is symmetric, that means the proposal probability is the same for both starting from Z prime to Zn and from starting from Zn to Z prime. So they're canceled out. Okay. That means the acceptance probability is only determined by the ratio of the joint probability, joint model probability evaluated at the candidate and the current sample, the current state. Right? An interesting thing is that if this guy, the numerator is bigger than this guy, so basically means if Z prime fits the data better, increase the whole joint probability, you will always accept Z prime as the next state, right? This is kind of like encourage you to move toward the high density regions. Okay? That's a known property for the symmetric proposal-based metropolis algorithm. Any questions so far? Okay. So now I want to talk about the problem or severe issue of the metropolis hastening algorithm. I mean, the naive metropolis hastening algorithm typically use some symmetric proposal distribution. So you might have seen this before. People usually call this as a random walk behavior. So why the metropolis hastening algorithm usually is so costly and so expensive, right? Because the reason is as follows. So we know that given the data, your target distribution, suppose you have like flat prior distribution, right? Once you get data, you can imagine that this information come in, it kind of like give you more knowledge. So your posterior distribution is much more concentrated, right? So you can view like if your prior is very, very flat, that's kind of like uninformative. After some data is failing, like you can imagine the posterior will be quite concentrated in some small regions. Right? And you have an infinite number of data, your posterior might concentrate to a point estimation. That's something we have discussed before. Right? The more data you have, the more concentrated or more narrowed down of your high density regions of your posterior distribution, right? Does it make sense? Okay. But the problem is that when you use metropolis hastening algorithm, right, every time you need to generate a candidate, right? When you generate a candidate, you just use symmetric, Gaussian, whatever. You actually, it's kind of a random try. You don't know which places are the high density regions for the true posterior, which places are the low density region of the true posterior, right? So that means for many samples generated, or many candidates generated at low density regions, you have to reject them. Why? Because imagine this is your true posterior, right? So if you want to generate samples from your true posterior, of course, you're gonna have dense samples in high density regions, right? You have very sparse samples at low density regions. There may be a lot here, and maybe a lot, far more large samples here, right? And we will compute the histograms. It will better approximate the true posterior, right? So that means in a target posterior, when it generates the samples, they're kind of like evenly, it's unevenly distributed. However, when you use metropolis Hastings like symmetric Gaussian, right, the chance you generate a candidate in the high density region and low density region is kind of same. Okay? So that means you're gonna throw out a lot of samples or candidates which stayed in the low density regions, right? Like for example, if this high density regions, we need 100 samples. And then in this low density region, it might just need 5. But if you use like naive proposal, you're gonna generate 200 samples, right? 100 here, 100 here. And for those samples in the high density region, you have like very high probability to accept them, right? Because they're increasing the likelihood, right? The whole data likelihood. But for this guy, you're gonna discard 95% of them because the acceptance rate is really low, right? And most of the cases you just reject them. But computing those candidates is costly, right? I generate 200 samples, but I kind of like threw out 50% of them. That's a huge waste of the computation. That's why it's called random walk behavior, because when you generate the candidates, you just do some blinded things, random trial. You jump here with equal chance, and then you got on average you got a large chance to reject your generated candidates. That's where it is costly. Does it make sense? Any question? That's what I call it, random walk. So I like say is random shooting. The target is there, but you don't have any information, prior knowledge to guide you to shoot around that direction. You got an equal chance to shoot any direction, right? In 360-degree, right? And of course, in most of your bullets are just wasted. Okay? And intuitively, if the data or someone or you got smart mechanism can help you, can tell you, okay, you should shoot along that direction. You're gonna save a lot of bullets, right? And your rate, your hitting rate will improve a lot. Right? In here, in our case, it will be like the acceptance rate will improve a lot. Okay, so now let me read through this. So why the random walk behavior is not good? Because in MCMC sampling, we want to collect samples that fit the target posterior. Right? In other words, their histogram should be more and more like the posterior. That means we require many samples on the high density regions and much less samples on the low density regions. However, if the proposals are generated like a random walk through the sample space, right, a great many proposals will be discarded, right, because most of them will be in the low density regions, and their acceptance rate will be fairly low. Then those samples, when they discarded, it means much computation cost is wasted. So how can we improve that? Actually, you see that many research about Markov chain Monte Carlo sampling is try to reduce the run and walk behavior. It's try to smartly leverage the information inside your drawn distribution to guide you to generate samples, generate candidates which are more likely to be accepted.
What is the direction according to more chance the direction according to the joint solution?
Yeah, that's there are several works trying to do that. But again, I mean, you need to you can come up with whatever proposal distribution, and you need to pass the acceptance test to ensure that you satisfy detail balance, to ensure that your chain finally converges to true posterior. And under this constraint, you can freely design whatever way to generate the proposals. And later we'll talk about like hybrid Monte Carlo, Hamiltonian Monte Carlo. It is indeed leverage the gradient information to get the new proposals. Okay. So I want to use this simple example to illustrate as well, right? Although we have a emphasize. So if we use symmetric Gaussian, right? So if you look at, if this is your current Zn, so you got the same chance to get a sample at here and get a sample at here, right? So we know that when you use symmetric Gaussian, then when your new candidate increase the likelihood, the whole joint probability, it will have an acceptance rate 1, right? However, if it decreases the likelihood, right, the acceptance rate will decrease a lot, right? However, the chance that you get you get candidates which are definitely be accepted, and you get candidates which are rarely be accepted is roughly the same. So basically, you can imagine starting from here or surrounding, you can generate 100 samples here, 100 samples here, like 200 samples. Well, all the samples are accepted in this region, right? But samples or candidates up here, like may only leave like 5 or 10, right? So that means 90 samples on this side generated by a proposal are just discarded. That's the waste, because you cannot guarantee you always generate a new candidates on the right-hand side, to the right of here, right? Because you don't know if you just use a symmetric Gaussian, right? You don't know if you don't know on which side of my Zn is gonna increase the likelihood. Okay, so here's the general metropolis hastening algorithm. As we discussed, it often suffers from the run and walk behavior. So next, we're going to introduce an upgraded version. It's called deep sampling. Okay. So deep sampling, later we'll see, is kind of like special type of metropolis hastening algorithm, but it guarantees your acceptance rate is 1. Okay, so what is deep sampling? It uses a conditional distribution to sample each single or subset random variable in a model. So acceptance rate is always 1. It is always a good choice if your conditional distribution is tractable and easy to draw samples. So what does that mean, right? In general, suppose this is a latent random variable, right? And given the data D, you got the drawing distribution P of Z and D, right? Your goal is to generate samples from the posterior distribution of Z given D. Right? So the deep sampling is simply to cyclically or alternatively to draw each element of Z. So each time, for example, if I want to draw a sample for the ith element of Z, I'm gonna use a conditional distribution. That is conditional on data as well as the current sample of all the other elements in Z. Right? And then here's the definition of Z not I. Z not I just all the Z elements except Zi. Right? And then once you get a sample of state for Zi, you just fix Zi and all the other elements to generate Zi plus 1, following the conditional distribution as well. You just keep doing this until you get new samples for every element in Z. You actually get a new sample for Z, right? And you just do this. This is like mean field. The procedure is like mean field version inference. But every time you're gonna use this conditional posterior to generate new samples. It's fairly easier. But the problem is that you need to ensure that this guy is tractable, right? And it is easy to generate samples. If you cannot compute this guy, this conditional posterior, well, you cannot use deep sampling. So now we list the algorithm steps, right, to give a more clear description. So we're gonna randomly initialize your Z. This just means the first state or the first sample in our chain, right? So Z11, ZM1, right? So in each iteration, meaning that each iteration is generate one whole sample of Z. So we're gonna first fix Z2, Z3 to Zm. We get Z1, right? The first element of Z1, a new sample for the first element, Z1, which we denote by Z1 n plus 1, means that, okay, you got a new sample at the next iteration, right? Next state, right? And then you just replace Z1 by the current sample and also fix Z3, Z4 to Zm, right? And then you sample Z2. Then you got a new sample for the second element of Z. You just continue doing so until you got a new sample for the last element of Z. You finish one iteration. And then you just keep doing this until burning, and then you collect samples. Okay, any question regarding the algorithm procedure? Okay. So a more commonly used approach is not to partition the random variables. Not to sample each individual element alternatively. Instead, we can partition the random variables into subvectors. Right? We can partition them into T groups. Right? Each group might contain one or several elements in Z. Then you do this alternative sampling. As long as you can compute the conditional posterior of each subgroup, given all the other variables in Z and data, you can do that. And this is also called a block deep sampling. So we want to use a specific example to showcase how we conduct deep sampling so that everyone has a more concrete idea about this. Right? So very commonly used task is called matrix factorization. So matrix factorization is kind of basic component in online recommendation. So what's the goal of matrix factorization? Suppose this is a kind of like a user movie rating matrices. So basically you can replace it by user product rating. Right? You got a bunch of products, you got a bunch of users, and some users are kind of like very willing to express their opinions about that. They're going to rate that. Right? And actually, those information are really, really important for online companies, online e-commerce companies like Amazon to improve their recommendation accuracy. So, suppose you have collected those ratings, right? And this rating matrix is really very sparse, meaning that in many entries, you don't know the ratings. You want to predict rating. If user 2 on our model, the prediction is that user 2 likes the movie very much. That means it might give like 5 rating of 5. Then we're gonna suggest or recommend movie 3 to that user. Right? And similar thing happened for products, right? So if you have some model, collect the information of these things, and you can make prediction about the rating. The higher the rating, the more like the better of that product you're gonna recommend that, so the user are more likely to consume or buy that product. Right? So we want to use a Bayesian or probabilistic model to do this. Like, how can I do that? For each user I, we'll introduce a feature vector, a latent feature vector. Well, you can specify the dimension of k, right? Like 3-dimensional, 4-dimensional, whatever. This dimension corresponds to the intrinsic properties of the users, like interests, like preferences, like income, all kinds of things. Right? So for each user I, we're going to introduce a latent feature vector ui to represent the properties of user I, right? And also for each movie G, we'll introduce another key-dimensional feature vector V of G to represent the properties of movie itself. It might correspond to rounds, the directors, and if it's good and business movies and whatever, right? So we can assign a Gaussian prior. It's very simple prior for the representation or latent feature vector of each user and each movie. Then, given the feature vectors of the user and movies, we model the rating through a Gaussian distribution. So basically, we sample the rating from a Gaussian where the mean is the inner product between the user feature vector and the corresponding movie feature vector with some variance tau. And then suppose you have observed a set of user movie ratings, that is pairs of the user and movies, right? So you can write down the joint probability, which is the prior of the user feature vectors, prior of the movie feature vectors. They are both Gaussian, standard Gaussian, right? And then this is the likelihood, right? It goes through every observed entry in this rating user movie rating matrix, and each entry, the rating values are IG, right? It's sampled from a Gaussian distribution with a mean as the inner product between the corresponding user feature vector and the movie feature vector with some noise variance tau. So once we write down this joint probability, right, we want to infer the posterior distribution of the user representations and the movie representations. And once we get that, you know, for some unobserved entry, right? See, for example, user 2 has never watched movie 3, right? We can predict the possible rating user 2 will give movie 3, right, from our model. So the problem is how do we estimate posterior distribution of user 2 and movie 3's latent feature vectors. Okay. One convenient way is to keep something. We can use keep sampling to sequentially sample each UI and VG. So you can imagine that, okay, our posterior distribution, the latent random variables includes all the users' feature vectors, all the movies' feature vectors, and the given data, right? And this guy does not have any analytical form. Right? Although you might see a Gaussian here, right? You might see a Gaussian here, but remember, you can have a Gaussian prior distribution over UI and a Gaussian prior distribution over VG. The Gaussian multiply Gaussian is not Gaussian. So you're not able to compute the closed form of the posterior distribution. But if we condition on any movie, all the movies, then you compute the conditional posterior on a particular user, the UI, right? And you condition on all the movies feature vectors and all the other users feature vectors, and also data and noise. what is the conditional distribution? It is Gaussian, right? Why? Because now this guy is fixed. And it's fixed, then it's just a linear Gaussian, right? It's just linear Gaussian, you multiply, but of course UI, the particular user I might rate a bunch of movies, but because all those movies, that guy rated their feature vectors are fixed. So actually they're all Gaussian to UI. We multiply a bunch of Gaussian for UI and also the prior, which is also a Gaussian, and you merge them together using the square completing trick we discussed before. It's Gaussian. It's pretty straightforward. And similarly, condition on for each movie G, right? Conditional on all the other movies and all the users, the conditional posterior will be Gaussian as well. Why? Because the user which it performs dot product with VG is fixed, right? So you can view like it's a linear transform of VG in a Gaussian likelihood. And then you multiply other Gaussian together, you manipulate the terms together, you end up with a Gaussian for VG.
Consider all the UIs together, all the UIs fixed, and it is the same.
Yeah.
One. You are considering UI one. You can separate, consider all UIs together.
Oh yeah, you can do that. Yeah, I'm just saying some particular example. I mean, you can freely partition the latent random variables according to your design, like you want to maximize the efficiency, whatever, right? But here I just want to emphasize the case that the joint posterior doesn't have any closed form. However, conditional posterior is very easy to compute. That's the benefit, and there's places where you can apply deep sampling. And indeed, I mean, in practice, people use deep sampling to do that. It's indeed kind of like a group all the users and group all the movies, and they do the alternative update on both groups. Okay, any question? That depends on your need. Like the benefit of deep sampling or the Bayesian way is that it always gives you a posterior distribution. You can draw a distribution of the representation for the users. As we mentioned before, actually in many recommendation system, you want some uncertainty calibration on that. I think I gave the example before, right? Like if your confidence, so given this posterior distribution, I can actually calculate for a particular VG, the chance that your rating is bigger than 3 or bigger than 4, right? If the chance is bigger than 5 or bigger than 4, at least bigger than 4, is high, like 0.9, then I'm gonna recommend that movie. Right? However, if this chance is relatively low, like 0.6, and then it might not be very interesting to recommend that. I'm gonna random pick a movie to give that user to give some freshness. So this uncertain calibration is very important and useful in the recommendation system. Of course, if you want to use SVD, it's fine. I mean, it's kind of pretty standard technique as well. Any other question? Okay, great. Hopefully this simple model can give you some concrete idea how to apply deep sampling and when should we apply deep sampling. Okay? So now we want to show why deep sampling is correct. I want to ensure our deep sampling indeed gives us the true posterior in the end. Right? So first, we need to look at what is the transition kernel. So the transition kernel essentially is just a product of this bunch of conditional posterior probabilities. Right? You condition on Z2 to M sample Z1, and then condition on the new sample Z1, Z3 to ZM to sample Z2, and condition on Z1, Z2, those new samples, old samples for Z3 to ZN to get next until you finish generation of the new samples for every element in ZN. Right? So suppose you have the M steps. This is your transition kernel. So the correctness of Gibbs sampling can be justified just looking at the invariance property of the chain. So basically, we even do not need to consider differential balance. We just try to examine if the target posterior is indeed invariant to the chain. Right? Remember, differential balance is just a sufficient condition to show that your chain is invariant to that posterior. Right? But here we can directly show this guy is directly the chain is directly invariant to the target posterior. Like, how can we show that? It's actually extremely simple. Because suppose, like, at any step n, right, your current Zn itself, or the n state of your chain, is really generated from the target posterior, right? Respect the target posterior. Now, given Zn, you always use a conditional posterior to generate the next element, right? So that means if you look at every step, like the joint distribution of this new element at Z1 n plus 1 and all the old elements, they will follow target posterior as well. Right? Why? Because if Zn is from target posterior, then your Z2 to Zm, those m minus 1 elements, will fit target posterior as well, right? Will follow target posterior up. And then you condition on them, and condition on them and condition on the true data, you generate Zn plus 1. Right? Their marginal, their joint distribution, of course, will follow the target posterior. Right? And then you can see that this vector, even just with a few new elements, they jointly follow target posterior. Right? Every step it follows. So finally, your new vector, which consists of all the new elements in your Z, will follow the target posterior step. That's it. Nothing else to show that. So, but this just show the invariance. That means the target, if you use conditional posterior to directly generate samples in your chain, then your chain guarantees to be invariant to the true posterior, but you have to also ensure the ergodicity. Right? And if you're dealing with continuous distributions, meaning that your random variable itself, the values of random variables are continuous. And then a sufficient condition is that as long as none of your conditional distribution is 0 anywhere in the sample space, like a Gaussian is not a Gaussian distribution, the density is not 0 across the whole input space, then that's fine. That guaranteed your chain. For example, your conditional distributions are always Gaussians, then it guarantees that your chain is not is ergodic. You don't need to worry about it converges to different distributions, right? Or it might converge to like 2 separate distributions. You won't worry about that. However, there could be some cases that this sufficient condition is not satisfied, like especially when you have some discrete random variables, your condition distribution might not be non-zero, might not be non-zero everywhere in the sample space. In that case, you need to explicitly prove the ergodicity. Any questions so far? I mean, regarding the understanding of this give something, it's pretty. I believe it's pretty standard. It's pretty straightforward. Okay, and then we want to draw the connection between give something and entropy hastening. Right? So we show the correctness of give something just to look at the invariance property of the chain. Right? We can show that okay, the chain itself is indeed invariant to the true posterior. Right? But if we want to use the detail balance and use the steps conducting entropy hastening to look into the give something, you'll find that actually each iteration of the give something is equivalent to multiple steps of entropy hastening hastening updates, and each step is acceptance. The acceptance ratio is acceptance probability is simply 1. Right? To see this, we can look at one step, right? And without loss of generality, we can sample the first element and look at where is the proposal distribution, what is the acceptance probability, right? And then you see that the other elements are generated in the same way. So suppose this is your current state or current sample Zn, right? It consists of m elements, right? We want to just draw a new value for the first element. That means we just update the first element. Right? So Z prime, you can imagine, like after the first step of give something will be Z1 n plus 1, right? This is a new sample for the first element, right? And then the remaining elements are the same. They do not change. Right? So, and we know that the proposal distribution, right? The proposal distribution is the conditional posterior, right? Which is Z1 and n plus 1 given Z2n until the m. Right? This is actually your proposal distribution. Right? Now we just want to look at once we use this proposal distribution to get Z1 n plus 1 and to constitute this to form this Z prime, what is the acceptance probability? Right? This is just the following entropy hastening step. We first generate a proposal or candidate, and then we just test if we're going to accept this candidate. So just to calculate acceptance probability, right? So which, this mean of 1 and this ratio, and the denominator is that you're going to starting from the joint probability, which is evaluated as the n, and then condition on the Zn, you generate a new sample. So now actually we only generate one element in Z, right? So this is the proposal distribution. Right? And similarly, in a numerator, we're gonna starting from this new sample Z prime, where there's only one new element, the first element, and all the other elements are the same as those in Zn. Right? We assume that they are sampled from the joint distribution, and given this guy to sample the original Zn, this is actually just to fix Z2 to Zm and sample Z1. Right? So to check this, we can divide this joint distribution, both numerator and both numerator and denominator by this guy. So this is just a marginal distribution of the second element to mth element. Right? When you divide it, you actually will see now this term becomes a conditional posterior condition on Z2 to Zm and evaluated at Z1 n plus 1. Okay. And this guy divided, it becomes the conditional posterior of Z1 when evaluated Z1 and D. And then you see that this guy and this guy is canceled, and this guy and this guy is canceled. It will give you exactly 1. I mean, the symbols here is a little bit messy, right? But when you manually check that, you see that it just cancel out. Like, again, I highly recommend you guys to verify by your hand, so it will kind of deepen your understanding of the connection between keep sampling and metropolis system. So that's keep sampling. So the benefit of keep sampling is obvious. So as we mentioned, right, it kind of largely reduced the random walk behavior, because every time I generate a sample, I guarantee the sample will be accepted. Right? But that does not mean keep sampling is the best. So even if you're able to compute the conditional posterior easily and sample them easily, that does not mean that keep sampling is efficient to construct the whole posterior, reconstruct posterior. Why? There's a problem. It's called inefficient exploration issue of keep sampling. That is the high correlation issue. What does it mean? It means that, again, this is your joint posterior, right? You can imagine that given the data, your posterior is concentrated. Concentrated simply means in a posterior distribution, each random variables are kind of highly correlated, right? If it is loosely correlated or even independent, you can imagine the posterior should be quite wide, right? But if it's concentrated, it usually means those variables in a posterior distribution are highly correlated. So you can see that if you use the conditional posterior to sample a new element, the range of the new samples are quite restricted, because it's kind of like highly bound to the other values, right? They kind of put a very large or strong constraint of the range. Right? To see that, you can use a Gaussian distribution as an example. Right? So if you have like 2 variables, right? In the prior space, well, it could be a standard Gaussian. That means Z1 and Z2 are just kind of orthogonal. You can move around like freely. However, if you look at the posterior space, that means we will compute a conditional Gaussian, and also the posterior covariance. Okay. Suppose this is still Gaussian. You can imagine that this covariance is not identity or diagonal at all, right? It's kind of like skewed, right? And then your posterior distribution, if you still remember the formula, it's kind of like covariance from Z1 to Z2, and the covariance of Z2. Let me use variance. Z2 inverse and Z2, right? And then if you look at covariance, is covariance of Z1 itself subtracted by something. Covariance Z1, Z2, covariance Z2 inverse, covariance Z2, Z1, right? So in the prior space, the covariance is this guy, right? However, if you condition of Z2, you need to subtract the prior covariance by something. Right? You actually reduce the covariance. You reduce covariance, that means your posterior, the conditional posterior has a much smaller variance. That's why the range of Z1, the value it can take, statistically is highly constrained. You cannot move too far away from Z2 or some distribution determined by Z2 or conditional Z2, your Z1 might be highly restricted. That's why you can only explore a little bit, although you definitely will accept this new proposal. Right? But if you want to explore the whole space quickly and efficiently to recover the whole posterior, it is hard. That's the issue of the deep sampling as well. Okay, thanks everyone, and see you on next Tuesday.